Welcome to the electrostatics lesson on static electricity and Coulombs Law. Static electricity is the imbalance of electric charge on the surface of a material. The key here is that it resides on the surface. More to come on that throughout the unit. And in order to understand static electricity, we first have to understand the basic atomic structure in solids and the free charge carriers that are free to move in a solid. If we take this diagram of a helium atom, for example, and we know it's helium because it has 2 protons in its nucleus, 2 neutrons in its nucleus, and it's a neutral atom, so it has 2 electrons orbiting the nucleus. We can see that the protons and neutrons are bound in the nucleus and not free to move. Basic chemistry, atomic understanding tells us that if we change the number of protons in the nucleus, we change the material, we change the element, we change the substance. So clearly, static electricity cannot be the movement of positive charge in a solid. Because if positives moves, the material itself would change during that movement. So static electricity simply has to be the absence or excess of electrons on a material, since electrons are the only free charge carriers that can move in a substance that is solid. Okay, that is really, really important. To demonstrate that, we have a device called an electroscope. As pictured here to the right, an electroscope simply has a knob at the top that passes through an insulating material down into the inside where air is prevented from disturbing the gold leaves that are hanging straight down here. And what is pictured here is a neutral electroscope. Let's take a look at what a positive rod brought near a neutral electroscope would do to the electroscope leaves itself. Here's a simulation of an electroscope and a positive rod that is going to be brought near the electroscope. On the electroscope we have a bunch of charges. We have the positives and the negatives, and you can see that for every positive charge there's a negative charge. Therefore the electroscope has a neutral charge at this time. Watch what happens as we bring the positive near that electroscope. Note that the positives don't move. The positives stayed exactly where they were, and the positive of course represents the protons bound in the nuclei of those atoms. However, electrons, being free charge carriers, are attracted to positive and would go up to the knob of the electroscope. What this does, of course, is creates 2 leaves that have absence of electrons. Absence of electrons is positive. What does positive do to positive? They repel. Therefore, the 2 leaves of the electroscope diverge. Therefore, if we draw a before and after diagram, the before diagram would have our neutral electroscope with many pairs of representative charges. Keep in mind these are only representative charges. There's actually nearly an infinite amount of charges on the electroscope itself. So the charges that are shown here are just a representative set. If we bring the positive near the knob of the electroscope, it attracts the electrons out of the leaves and causes an absence of electrons in the leaves of the electroscope. Absence of electrons creates positive charge. Positive repels positive, and the leaves diverge. Let's now think that through and analyze what would happen if a negative rod were brought near a neutral electroscope. So once again, we start out with our neutral electroscope, and this time we're going to bring a negative near that. Well, what would a negative do to the free charge carrying electrons that are represented in this diagram? As you can see, the electrons are repelled away from the knob and pushed into the leaves. What this does is gives the leaves extra electrons than what they had before. And an excess of electrons creates a net negative charge. And what does negative do to negative? Repels. So the leaves diverge. So now again, if we start with a diagram, this is what it looks like before the negative rod approaches with a neutral electroscope. And afterwards, the electrons are pushed into the leaves, creating a net negative charge on each leaf. And negative repels negative, and the leaves diverge. All right, hopefully this illustrates for you the movement of static charge and illustrates the point that static charge is only the absence or excess of electrons, and that positives do not move. Next, let's talk about the sharing or movement of electric charges from one object to another. Let's suppose we start off with two identically sized spheres, and it's important in this conversation that the spheres are identical. As mentioned earlier, electric charge, static electricity, resides on the surface of the object. So if these objects had different sizes, they would have different surface areas in this conversation, then would be different. But since they're identical, they have identical surface area. We have one object that has a bunch of represented charges here on our left, and you can see that these 4 positive charges are balanced out by 4 electrons. But these 4 positive charges do not have electrons. Therefore, we would say that this object has a net positive 4 charge. There are 4 more protons than there are electrons. For our object over on the right, it has 8 representative charges, all without electrons. So we would say that that object on the right has a net charge of positive 8 elementary charges. What if we brought those two together, touched them, and then separated them? Well, if we brought them together, electrons would flow from one object to the other until there was no difference of charge between them. So if we take and move this electron over to the one on the right, the one on the left now has 5 positive charges, while the one on the right now has 7 positive charges. If we take and move another electron over to the right, the one on the left now has 6 positive charges. The one on the right now has 6 positive charges. There's no difference no longer, so electrons stop flowing. So here we see that both objects end up with a net positive 6 charge. Can you figure out a way to determine what the net charge on each would be without individually moving electrons? Well, if you said that the charge that will result on each is the average of the charges of either, then you would be correct. Positive 4 plus positive 8 is positive 12, divided by the 2 objects that were touched is positive 6. Let's practice that now with not just elementary charges, but with charge in general, which is in units of Coulomb. If the object on the left has a positive 10 Coulomb charge, and the object on the right has a negative 5 Coulomb charge, what would the charge on each be if they were touched and then separated, provided that these 2 objects are equally sized? Well, quickly here, we just got done saying that it's the average of each. So if you take positive 10 plus negative 5, that is positive 5, divided by 2, would be positive 2.5 coulombs for each object. Next, we're going to talk about converting One elementary charge was found by Robert Millikan to have a charge of 1.60 times 10 to the negative 19 coulombs. So if you wanted to figure out how many coulombs a given number of elementary charges were, or how many elementary charges were as a given number of coulombs, you could use this as a conversion. It was also decided that a coulomb of charge would be designated as a unit to represent a larger number of elementary charges. And that is 1 coulomb is 6.25 times 10 to the 18th elementary charges. You could actually use either one of these to convert from elementary charges to coulombs. Most remember that 1 elementary charge is equal to 1.6 times 10 to the negative 19 coulombs, simply from the emphasis on the Millikan oil drop experiment. Lastly, let's discuss Coulombs Law. Coulombs Law, in words, states that the electrostatic force is directly proportional to the product of the charges and inversely proportional to the square of the distance between the centers of those charges. If we dissect that law and where it came from, Coulomb is saying that the electrostatic force is directly proportional to the product of the charges. The next statement is that the electrostatic force is inversely proportional to the square of the distance between the centers of the charges. R does not stand for radius, it stands for distance between the charges. If we combine both statements, we see that electrostatic force is directly proportional to the product of the charges and inversely proportional to the square of the distance between the centers. However, those two sides are not an equality. They're simply directly proportional. How do we accomplish that? Well, Coulomb tediously graphed various quantities trying to get a direct relationship, and it wasn't until he plotted electrostatic force on the y-axis and Q1, Q2 over r squared on the x-axis that he got a directly proportional relationship, a linear fit to his data. Well, the proportionality constant comes from the slope of the graph, and the slope, therefore, is called Coulomb's law constant. You will also hear it called the electrostatic constant, and is given the symbol lowercase k. Fe then became equal to k q1 q2 over r squared, where k is the proportionality constant for a graph of Fe versus k1 q2 over r squared. On your reference table, you'll also discover that k has a value that's equal to 1 over 4 pi epsilon 0, epsilon 0 being the permittivity of free space. We just substitute k, or just substitute the value of the electrostatic constant, which is k equals 9 times 10 to the 9th Newton meters squared per Coulomb squared. Where do those units come from? Well, up here in this equation, if we isolate that equation for k, we'd multiply both sides by r squared and divide both sides by q1, q2, giving this equation that we see here. Well, units of force are newtons, units of distance is meters, and since it's squared, it would be meters squared. And unit of charge is coulomb, and since it's coulomb times coulomb, that would be coulomb squared. Hence the units for the Coulomb constant, Coulomb's law constant, Newton meter squared per Coulomb squared. What is often done is also they really like to compare this to gravity. The two equations are similar. Fg equals big G m1 m2 over r squared, and F equals k q1 q2 over r squared. They're both inverse square laws. However, you may remember that big G is 6.67 times 10 to the negative 11. And so by examining the constants alone, we see that the electrostatic constant is 10 to the 20th times larger than the universal gravitational constant. That is why gravity is the weakest of the fundamental forces, and electrostatic force is stronger than gravity.